continues the Gaussian process. The Kalman filters seem to come in 1,000 different varieties, but they're actually just simple linear Gaussian models. They're a lot simpler than all the Kalman filter texts would have you believe. All apart from one, actually, there's a great book. If you are interested in this area, the book to read is Simo Sarkar's, and it's available from his website. And it really, he understands Gaussian processes, he understands Kalman filters, and he really does a great job of summarizing this literature. I think I would almost go so far as to claim it's the only readable reference for me in this domain. Bayesian filtering and smoothing. Simo's spoken at the summer schools in Sheffield, and one of the really nice things is the book's in PDF format on his website. So if you want to understand more details about Kalman filters, state space models, how they relate to Gaussian processes, Simo's, I would say, probably the leading expert in the world in this area. And his book is fairly recently published, and it's super readable. So much better than most books in this area. Covers particle filters and other books, other things like that. So really worth having a look at. I love that book. Okay, but I'm going to take quite a simplistic point of view, and that is that Kalman filters, well, they're based on an initial, to build a Kalman filter, you start by building a Markov chain. So a Markov chain is something that exhibits the Markov property. It's in the example I've got here, to get a Markov chain, all we do is we say that the value of some state vector x, so this is some latent state, is given by the value of that state vector at the previous time point plus some Gaussian random noise. So the lecture notes, Maurizio's emailed them around. So what that means is we find that xi is given by a Gaussian distribution with a mean of xi minus 1 and a variance of alpha if epsilon is distributed with a variance of alpha. And then once we've defined that, we just need to define an initial state, which typically we might say is Gaussian, although I'll take it to be 0 in what comes next. And then you've got a Markov chain for these latent states. You've got a distribution, a probability distribution over these discrete values, and it's Gaussian based. So it's defined, importantly, Markov systems are defined by an initial distribution and a transition distribution. That's how you define a Markov system. So the Markov property is that xi only depends on the previous state. It doesn't depend on states before that. Okay. So what does this look like? Well, if we're starting at state 0, and then we sample a corruption from the Gaussian random variable, which in this case is minus 2.24, and then we keep adding. So then we get the next one by sampling another corruption, so we add that on. We get an evolving state like this, yeah? And x9 is just the sum of all those Gaussian epsilons that came before, yeah? So, remember, multivariate Gaussian properties. If z is drawn from a Gaussian distribution with this way, and x is given by a Gaussian distribution which is x is given by z multiplied by a matrix W plus some bias B, then we know that x is also Gaussian distributed with the mean given by W mu plus B, and the covariance is given by WCW. Okay, just a reminder of those multivariate Gaussian properties that underpin pretty much everything we're doing. So, and there's the simplified form. In particular, if we've got this as a spherical prior, then we get this thing out as a sigma squared WW transpose. Now, what I want you to see is that the way we define that Markov chain is such that x is related to epsilon in this way. So this is a lower triangular matrix of 1s. And x1 is given just by, because x0 was the initial state, x1 is given by just this 1, 0, 0, 0 times epsilon 1, epsilon 2, epsilon 3, epsilon 4, epsilon 5. So this just picks out epsilon 1. x1 equals epsilon 1. x2 equals 1 times epsilon 1 plus 1 times epsilon 2 plus zeroing out everything else. x3, x4, x5. Yeah, everyone agree? So, of course, this means that x is equal to L1, where L is a lower triangular matrix of 1s, times epsilon. Now, since we know that these two things are linearly related, x is equal to L1 times epsilon, we now know that x must be a Gaussian process. And furthermore, we can compute its mean, the expectation of, this is what we've just been doing on the board. The expected value of x is equal to the expected value of L1 times epsilon, which is just equal to L1 times the expected value of epsilon, which is 0, because epsilon is distributed according to a Gaussian with 0 mean and variance alpha. And then to get the covariance, we just go through the same process and we recover that multivariate Gaussian rule, that the covariance is equal to alpha L1 transpose. So, what we have is that x is distributed as a Gaussian with 0 mean and covariance given by alpha L1 transpose. Now, what I want to do is turn this into a process, because that's a discrete time setup. Yeah? So, this is our covariance over discrete times. But typically with Gaussian processes, we want to know what this would be over continuous times. And the way we're going to do that is we're going to assume that that variance grows linearly with time. I mean, you can prove that it would, but we'll just assume it does. And the reason for that is that the sum of two Gaussian distributed random variables is distributed a Gaussian with the sum of the variances. So that implies variance grows linearly with time. Now, if the x variable's movement is additive over time, that means the variance will scale linearly with time. So what I'm going to do is I'm just going to substitute, I'm going to take the discrete value and say, well, we're going to add in this time interval, delta t. So what delta t does is it says, so what's going on here is I'm trying to subdivide that initial system. So I start out with time is 1, and then time 2, and then time 3. And I'm trying to ask the question, what's going to happen between these times? And what I'm saying is that if we halve the time at which we look, 0.5, then the variance, if I want to sort of look in between here, then I can say what's going on is, to get to here, really, there was two Gaussian variables summed. So at here there was an epsilon, sort of an epsilon prime 0.5 and an epsilon prime 1, and the sum of these two is equal to epsilon 1, what we sampled in the first place. In order to make the sum of these two scale in the correct way, the variance of epsilon prime must be half the variance of epsilon 1, yeah? So if I want the time interval at 0.5, I basically say that this guy here is sampled with variance delta t, where delta t is my new time interval, times alpha. Does that make sense? Okay, so I can keep doing that. I can keep subdividing and the same thing's true. So I've just introduced the delta t to allow me to ask the question, if my delta t is now 0.1 or 0.5, to now allow me to ask the question what's going on at all the intermediate intervals. Now, let's take a look at what this means. If we look at the covariance matrix, it's given by alpha delta t L1 transpose. Now, each individual element of that covariance matrix, we want the covariance function, is given by alpha delta t Li. So this is the ith row of L1, and this is the jth row of L1. Okay? So this is the inner product between the ith row of L1 and the jth row of L1, because it's L1 transpose. Agree? Now, this inner product is always equal to the larger of I and j, sorry, the smaller of I and j, because it's basically an inner product of, if we're looking at the L1 vector like this, it's taking one row, inner producting with another row, where these are all 1s. So it's just multiplying all those elements by each other. Where they're 1, you just get the sum of the elements there, and where they're 0, in this case, they're 0, so those elements get summed out. So the answer to what this inner product is simply the minimum of I and j. Yeah? But delta t times I, so we're saying that we've got these time intervals delta t and measurements I, 1, 2, 3, 4, 5. Delta t times I, or delta t times j, is just the time at I, or the time at j. So delta ti is ti. So in other words, the covariance is the minimum of ti and tj. Make sense? So we've now gone from this Kalman filter, which has given us, this Markov chain, I should say, and we've looked at what happens if you do the Gauss Markov thing, and we recover that we get this covariance, which we've already talked about in the last session as being the Brownian motion covariance, which is no surprise because that Markov chain is Brownian motion, just bouncing around randomly in Gaussian directions, a random walk. Okay? People happy with that? So it has this form that you've already looked at in the labs. It looks like a sort of quarter of a pyramid. So this is the largest value here. Variance increases over time linearly, so the standard deviation goes up with the square root of time. And you get, because there's min, you get this sort of ridge down the middle. Then there's the samples, which we've already looked at. Now, here's a weird thing about this covariance. If you invert this covariance, you get a sparse matrix. So that is a weird enough thing that it's actually worth doing. Let's see. Do we have it close enough? I can't remember. I've got the IPython notebook up. Maybe we'll do that in the practical session, because it's a strange thing. Like you design a covariance, but it's not a strange thing. It's clear that it's going to happen. You design a covariance in the sort of covariance space, and then you invert, and you make it full. You invert it, and it turns out to be sparse. So it's tri-diagonal. It has elements down the diagonal here and off diagonal here. Can anyone explain why that's the case? Does anyone know what the sort of precision matrix of the Gaussian gives us? So some people call it partial correlations, but I'd like to think of it as the conditional independencies. The inverse covariance gives us the conditional independent structure. The partial relations between these guys. So what this is saying is that this point here is independent of all other points given the non-zero points either side. So given the point to the right and the point to the left, this data point here is independent of everything else. That's the Markov property, actually, marginally. So this structure is emergent because of the way we define the system as a chain. This is the Markov chain appears in the precision matrix. So the Markov structure comes out of that. Now, if you look at, for example, at the inverse matrix of the exponentiated quadratic, you see these patterns, right? So we're seeing that we do see some dominant structure on the diagonals. It's most affected by the things to the front of it and to the right of it, but there's still partial correlations with data points at other times. I'm not sure how clear that is, but actually, I've got color blindness, which affects me when I look at this, but I hallucinate something here as well. Maybe it's not really there, but there's certainly something here, some yellow colors, right? So you've got these structure here in the exponentiated quadratic covariance that actually turns out to be infinite. It's not Markov at all. It's infinite order Markov, which is related to that differentiability property. So it's non-Markovian, the exponentiated quadratic. So what's kind of interesting about that is, or this particular covariance, is this is where two worlds collide. Large numbers of systems are approximated as Markov processes with this Markov property, which means you only have to specify the initial state and the transition state, the transition probabilities, yeah, which is what we've done. Equally large number should be seen as Gaussian processes. People don't always talk about them as Gaussian processes. But in the Gaussian process, you specify the mean function and the covariance function. So you specify a different two things. Yeah? So if you're building Markov modeling, you specify your initial state, your transition. If you build a Gaussian process, you specify the mean function and the covariance function. When worlds collide is when you've made those transitions Gaussian in the state space model or the Markov process model, you get a Gaussian process as well. So you get a class of models that is both a Markov process and a Gaussian process. Now, if you constrain yourself to first order Markov, then there's only very limited numbers of covariance functions you can represent this way. But the sort of work Simo Saka is doing is where you allow that Markov order to increase by augmenting your state space, and then you can represent quite a lot of, for example, these Matern covariance functions, you can represent them as state space models, and that leads to advantages in terms of computation. We're not going to talk about the details much more beyond that. But just to give you this connection between this world of state space models, where you're often defining Markov properties, and the Gaussian processes. Now, this Gaussian process cannot be represented as a state space model exactly, but it can be very well approximated by a state space model. It can't be represented as a state space model because it needs an infinite dimensional state space in order to do so. It has an infinite memory. But in practice, its memory isn't very good over the long term, so you can approximate it. So for example, remember I said that the Matern covariances, if you increase the Matern order, if you increase the differentiability of the Matern very large, then it becomes pretty indistinguishable from the exponentiated quadratic, so we don't tend to use those. But a Matern covariance can always be expressed as a state space model. So if you want something with high differentiability, you could use a high order Matern covariance. Okay. I've gone backwards. I think Max, the wheel on Max goes the opposite direction to Linux or something. So I keep going backwards. Okay, so in a Kalman filter though, we don't just have one of these processes, and we don't necessarily have this independence I'm about to put in, but you can extend this if you want to. What we have is a number of processes, and what I'm going to assume is those processes are independent. So we've got sort of 4 latent unobserved processes, you know, that are driving what we're observing in the multivariate world. So if the multivariate world is your heart rate, those processes might be what's going on the slides, what the temperature is, you know, whether there's anything stressful noise-wise happening outside, like a drill or something like that. Could all be affecting your heart rate, but they'll affect it in different ways. So we're saying those things are independent, and we assume the independence across this latent dimensionality so that we get a probability over a matrix of latent processes. So it's a design matrix style, so it has t time points and q dimensions, is given by this. Yeah, just independent across those q processes that are affecting our observations. Now, if we want to obtain our outputs, what we're going to do is we're going to say that the observed output is linearly related to those processes. So in other words, what we're saying about your heart rates is you react to these different things in a different way. Some of you are listening to the power drill outside, and that's affecting your heart rate more. Some of you are watching the slides, and that's affecting your heart rate more. But we expect your heart rate to be affected as a linear combination of these 4 different independent processes. And of course, because once we've fitted that model and worked out how that all interrelates, we can start cross-predicting about your heart rates, because we know that you might be affected by the